So remember that we're in this section, really the start of the chapter, talking about modeling. We're not doing that much qualitative analysis. We're not doing any numerical techniques or approximations. We're just showing you the answers. And we're certainly not solving any of this by hand, because if you remember, this predator-prey model cannot be solved by hand, all right? There are no analytical methods for this ordinary differential equation. All right, so we have a question for you, but before I ask the question, let's review something, right? What's the difference between these two differential equations? dp dt is equal to k times p, and dp dt is equal to k times p times 1 minus p over n. Now, hopefully by this point in the quarter, you should know what both of these equations are and what they represent and how they're different, right? This is just exponential growth, and this is logistic growth with a carrying capacity n. They're very similar, and again, we talked about how linearization helps us... Whoa! Well, October slipped on the book, and the book went kerplop. Your differential equations book is very heavy, by the way. Anyway, she's okay. The book, we'll find out. It doesn't matter as much. So this is logistic growth, and we showed by talking about linearization, right, that if p is close to 0, we pretty much have exponential growth, and if p is close to n, we kind of are decaying to that carrying capacity. All right, so if I asked you to modify this predator-prey model that we introduced in 2.1, or really introduced in 1.1, how would you do it? If I wanted the rabbits to grow logistically, okay? I want rabbits to follow logistic growth, or they would follow, let me be more accurate, right? They would follow logistic growth if there weren't darn foxes eating them. Well, again, notice that this is the growth part of the rabbits and the death part of the rabbits. This is the death part of the foxes and the growth part of the foxes. We're not changing anything about the foxes. They're dying unless they're eating rabbits. But we're going to say if there are no foxes, we want the rabbits to follow logistic growth. Well, what we would do is we'd make one tiny little change. Just 1 minus p over n. What n do we want to do? Oh, and we're using the letter r, so let's do that first of all. You could use any carrying capacity you want. I mean, it depends on the situation, but the book uses a nice number of 2. Right? And that's all that needs to be added, right? And all of a sudden, our model changes. That's the power of differential equations, is that you can make a tiny change. You want to add this thing? Okay, let's add this thing to the model, no problem. And of course, the solution is going to be much harder or more complicated or change a lot. But the power of differential equations is we can incorporate these details into our model much easier than like just changing a solution. All right. Think about, again, this exact thing, right? This was a small thing that we incorporated, and it came from something that was very logical. The solution looks very different between these two differential equations, but again, this is the power of ODEs. So let's remember what happened. So the original predator-prey model, right, had these delayed periodic functions where the fox population follows the rabbit population. They're all periodic. We had a phase portrait here, right? We had a bunch of solutions. Let's ignore the axes for now, but everything was basically oscillating and circling that equilibrium solution of about 1.1, 1.6. This is what our predator-prey model looked like if rabbits could grow exponentially without the foxes. Now, how much could this really have changed? Well, let's look at the equilibria. Remember, the old original one had equilibria at around 1.1, 1.6, and another one at 0, 0. What about our equilibrium solutions here? Okay. Well, and again, there was, yeah. All right. Well, let's consider. And let's maybe not just look at equilibrium solutions. Maybe we'll look at a couple other solutions. I'm not sure. All right. So again, is 0, 0 still a solution? It better be. If 0, 0 is not an equilibrium solution, we have some weird things happening right now. All right. And you can see, yeah, if I plug in R, everything's 0. This is just quadratic in R. If I plug in F equals 0, yep, everything's 0. So 0, 0 is still a solution. Right, 0, 0, still a solution. That's unchanged. What about the other equilibrium solution? Well, again, how do we do it? We said, okay, if R equals 0, what happens with F? If R equals 0, this first thing's 0, no problem. And all right, then F is also equal to 0. All right, we already talked about that. That's not interesting. But if F equals 0, what happens? Well, if F is 0, this whole thing is 0, and that's fine. This part is 0 as well, right? And if F is equal to 0, this is the only interesting thing happening for an equilibrium solution. We need this to equal 0. We know exactly when this equals 0, right? When R equals 0, which we already talked about, and when we're at our carrying capacity. All right. So F equals 0 means that R equaling the carrying capacity will also be a solution, right? That's a solution, equilibrium solution 2, 0. There's also an equilibrium solution of 10/9, which is the same as before, I believe, and 20/27. All right, which is previously we had 1.1 and 1.6. So the fox population equilibrium point got smaller, which makes sense because there's going to be fewer, the rabbits aren't going to grow as much. The fox population is going to be dampened a bit. So yeah, where did this come from? You could find it yourself. There's an exercise actually. The exercise is number 12 and actually section 2.2, but I think you all could actually do it now if you really wanted to. But you don't need to know where this came from, although I think you could figure it out. All right, so let's plot these solutions. Let's use numerical methods that we haven't covered yet to see what solutions would look like. Again, here's the phase portrait of old. What does our new phase portrait look like? Oh, wrong color. Let's look over here for now. Well, that's pretty different, right? This part is the same, right? If there are no rabbits, the foxes are going to decline down to 0. We still have that equilibrium point down here. That part's the same. Here has changed very notably, right? Instead of just a source at 0, we now also have a sink at our carrying capacity, which is again what we would expect. If F is equal to 0, R just follows the logistic growth model. This is our phase line for the logistic growth model. We've been drawing our phase lines vertical, but this is really just a phase line for logistic growth. But now notice that before, right? Before we had like all of these kind of solutions circling a slightly different equilibrium point. We don't have any periodic solutions anymore, right? Now all the solutions are kind of spiraling in a little bit. We're going to have a term for that later when we talk about different kinds of equilibrium solutions. But for now, just notice that they're kind of all spiraling into that equilibrium solution, which again is different. And if you look at these letters, right, these letters denote 4 different solutions depending on the different initial conditions. So here's one solution. If the initial condition is whatever that equilibrium point is, then yeah, the foxes and the rabbits are there's going to be balance. The fox population won't grow, the rabbit population won't decay. All right, equilibrium solution, that's what it means. And that's not a very interesting graph, so we didn't graph that. What if this is our initial condition? If this is our initial condition, then what happens is the rabbit population decreases and the fox population increases, right? We're going to the left and up. And then the rabbit population keeps decreasing, but there's too many foxes. So they don't have there's not enough rabbits, so the fox population is going to decrease. And then eventually the fox populations decrease enough that the rabbits are increasing. And again, we get the same kind of behavior, but instead of just going around in circles, there's something kind of tugging it towards the middle. And eventually we will approach kind of asymptotically we're going to approach that equilibrium solution. And in fact, we observe the same exact behavior no matter where we start. Okay. And if we could zoom in here, I say this with 90% confidence. If we could zoom in here, we're going to see some continued spirals, right? It's not like this approaches directly from the left. It's not that this approaches directly from the right, right? They are spiraling. It's just, we can only see so much from this just little picture. And we can see plots of all these functions, all these solutions over here. For example, for a solution curve C, oh, I did not put these in order. Oh, I put them in order and then I switched them because my camera's over here. I didn't want to block it. So letter B that we talked about, right? You can see what's happening. R, right? The rabbits, it's doing exactly what I told you. But now in this form, right? If we plot the actual solutions against time, then we can actually see how time affects these. How fast do these changes happen? All right. We knew the rabbit population was decreasing and eventually increasing and then decreasing again. But we didn't know how fast that was happening from looking at the phase plane, because just like the phase line, the phase plane never shows you how fast, right? We don't have like a big arrow over here and like a tiny arrow over here, but you can see that the change happens very fast at the start and then slows down. All right. So again, all of this comes from numerical methods. You don't need to know what these are going to look like necessarily, or necessarily even memorize things, right? But just knowing how to work with these models, finding equilibrium solutions. We're just mostly introducing different things about systems of differential equations. How do phase portraits look like? How do we compare phase portraits with the graphs of their solutions? Again, these solutions that we generated as numerical approximations, but all the same, how do these things interact? Could you look at this graph and create, right? Could you, sorry, this is C over here. This is the solution curve of C. Could you look at the rabbits and fox population in C and try to plot that on the phase plane? That would be good practice. All right. That sort of a thing would be good. And you can practice that however you want, right? You could just make your own solution curves. You know, say, all right, maybe I have one solution that, you know, looks like this, and the other solution look like this. What is that going to look like in the phase plane? And again, you'd have to label your axes, right? This is going to be T, and maybe this is going to be, I don't know, whatever you call it, X and Y. And then this one is X, and this one is Y. That'd be good, some good practice. You can make any curve you want. And then you'd go over here to the XY plane. This might be the first time in this whole class we've had an XY plane. And you see, okay, where do we start? Well, we start when y is 0 and x is some positive number. So we're going to start y equals 0, x is some positive number. What's happening over time? Well, first, x and y are both increasing. And then eventually, right, x starts decreasing while y is still increasing. And in fact, x is decreasing and y is increasing for the entire rest of this existence. So maybe, and they both seem to kind of asymptote. All right, so maybe we get something like this as our solution. All right. Eventually, or actually, hold on. Eventually x, right? X also asymptotes, so actually it would not be quite like that, right? So, right, we start up here, we go over here, and eventually both kind of stop. Well, if both stop, that would be some equilibrium solution over here. So this would be our start, and according to this graph, they both approach an equilibrium solution. So then this might be our equilibrium point. We know we're going in that direction. So that would be some good practice. All right. But that's pretty much what this video is about. In the next video, we're going to talk about something completely different. Dun, dun, dun. Or is it? Anyway, we'll talk about springs. I'm recording this in the fall, but there's a place for springs too. Ha ha ha, what a funny joke. Goodbye.